Hello guys, so we are here to discuss INMO 2025 paper. Paper was very nice, level was very good, especially geometry problem was a very beautiful problem. So we'll discuss solution to all the problems here, starting from question number 1. So I'll outline the solution of the questions first, and then one of the students here will come and detail the solution as they did in exam. So let us start with question number 1. It's a standard sequence problem where statement of the question is a 2k plus 2 and a 2k plus 1 is equal to 2 times 1 plus ak. Initial conditions are so this is what is required of the question, that we have to tell all those n where an upon n is an integer. Now when we see this question, there are lots of points that goes in mind. जैसे इसमें एक पॉइंट ये जाता है कि क्या हम इसको रिकर्सिवली सॉल्व कर सकते हैं या नहीं. कैन वी हैव अ क्लोज्ड फॉर्म फॉर दिस प्रॉब्लम, जिसमें ऐसे कि हमको ए के पता चल गया एग्जैक्टली ए के इज इक्वल टू दिस थिंग, सो दैट वी वुड नो द आंसर एग्जैक्टली. As it turns out, we can do that, but mostly if you see, that is not the intention of the problem. So second question is, what is the intention of the problem and how do we solve it exactly in the exam time? So for that particular thing, the obvious thing that we start with is we start finding value. A3 obviously attacking from here, it comes out to be 6. From there we see that there is a multiple of 2 coming. Then we try to find A4, A5, A6, so on and so forth. If you keep on finding for another number where n by n becomes an integer, yes, in this case A3 and 6, so 6 by 3 becomes 2. If you keep on finding, we see that numbers are in general less than 2n. Like say A5 is less than 10, A6 will also turn out to be less than 12, and A7 will become 2 times, once again using this particular thing, A7 will become 2 times 1 plus 6, and this will become 14. So once again A7 upon 7 will become an integer. So this gives us some clue. The answer is coming out here, and mostly if we see this being a linear function of ak and ak plus 1, this being a linear function of ak and ak plus 1, there is a very good chance that output for maximum value will be less than 2n. Just an will be there is a very good chance will turn out to be less than 2n. So by trying these values, we get some idea that the answer to the problem could be 2 to the power I minus 1. In the sense that when I becomes 2, this becomes 4 minus 1, 3. When I becomes 3, this becomes 2 cube minus 1, which is 7. So A of this particular value might give us correct answer. But how do we prove it? That this n by n is integer by using 3 steps. First step will prove that, so first step will prove that n is greater than n for all n, as we can see with examples, and it's easy to prove because even if we go by induction, these steps obviously show that this is true, but I'll show that. Step 2, n is less than or equal to 2n for all n. Alright, in case we are able to show these 2 steps, the obvious answer for an by n being integer will be those cases where n is equals to 2n. Right, so as a step 3, we'll try to find out those values of n where an becomes 2n. All right, so the steps are this one. Step 1, showing this by induction. All right, so these two steps will show by induction. Step 3, an equal to 2n, will try to find out those values of n where n becomes 2 times n, such that ratio of n upon n becomes 2. All right. So for example, if I want to show step 1, an is greater than n by induction, will show that for every value till n equal to k, this is correct. From k equal to 1, 2, 3, 4 till k, this statement is correct. So we'll have to prove for k plus 1. Now k plus 1 could be odd or k plus 1 could be even. If that is even, for example, then a of, say that number k plus 1 is equals to 2m plus 2, because it's an even number. So then that will be equal to 2 plus am plus 1. But we have already proven that for every number less than 2m plus 2, am is greater than m. So using induction, we can say that this whole thing is already greater than 2 plus m plus 1, which implies a of 2m plus 2 is greater than 2m plus 3 also, but other greater than 2m plus 2 for sure. All right. So we have already shown for even number. Similarly, we can show for an odd number. It's easy to see from here, right inside. Now the second step will prove an is less than or equal to 2n for all integers. For even integer, this will come out to be less than 2n. And for odd integers, there will be cases where it could be equal to 2n. Otherwise, we can prove this is less than or equal to 2n. And then last step, an equal to n, we have to find those numbers out. Then using binary sequence and maybe some other methods as well, we can easily find out that 2 to the power I minus 1, whenever all these numbers n are of the variety 2 to the power I minus 1, this will work. So I am leaving that part of the solution for the next part of the video, where student outlines the complete solution. And for that, I am inviting Om and Nishkarsh on the board to show me the complete solution. All right.
In first question, we need to show two important things, that ai is greater than I for all values of I, and it is less than equal to 2i. It is less than 2i for most of the values of I, and equal to 2i for some specific values of I. And so if it is not equal to 2i, then ai upon I is obviously not an integer. And first we'll show that ai is greater than I. We can easily show this by induction. For even m, we have a 2m plus 2 is equal to 2 plus am plus a of m plus 1, and base case 1 and 2 are given to us, they are obvious. For all even ai is strictly less than 2i, and we can show that by a simple argument. We will assume that a 2m plus 2 is the smallest even number. We will call all those numbers good numbers for which ai is equal to 2i. All those even numbers are good numbers, and we will assume that a 2m plus 2 is the smallest even good number. But for a 2m plus 2 be good numbers, both am and am plus, at least one of am and am plus 1 is even, and both of them have to be good numbers. So we can find a smaller even good number from here, which is a contradiction. So there exists no even good number. And now we will assume all odd numbers which satisfy the condition that ai is equal to 2i are good numbers. So we have the relation a to m plus 1 is equal to 2 2 सेकंड, पॉइंट रिलेशन क्या था? 2 plus 2 am and if we assume that a 2m plus 1 is a good number, then we can easily show that am is also a good number. So if I here represent a 2m plus 1 as a binary number, a 2m plus 1 as a binary number, 2m plus 1 as sorry, 2m plus 1 as a binary number, then we find that if we remove anyone from the sequence which is equivalent to going to am, has to be a good number, and if we keep removing ones, we should keep getting more and more good numbers, and if we get a 0 anywhere in the sequence, then it is a contradiction, because we have shown that no even numbers can be good. So our good number has to be a sequence of ones, and a sequence of ones in binary in base 10 will be 2 to the power base 2 will be 2 to the power m minus 1, and that is the answer to our problem. They are good numbers because like if we consider our first good number, which is 2 to the power m minus 1, then a of 3 will be equal to 6, and if we find all 2 to the power m minus 1, then it will be equal to 2 plus twice of a to the power 2 to the power m minus 1, and by for induction we will assume that all 2 to the power m minus 1 are good numbers, then a3 is base case is a good number, and then all subsequent cases can be shown by induction that all 2 to the power m minus 1 are good numbers.
First claim for this question was that for every ak we would have ak less than 2k plus 1. So we assume that ak is greater than 2k for some k. Now k can be of form either of the form 2m plus 1 or of the form 2m. We put these values in the formula which is given to us, that a 2m plus 1 is equal to 2 plus 2am, and a 2m is equal to 2 plus am plus 1 am minus 1. If it is of the form 2m plus 1, we directly get that am is also greater than am is also greater than 2m, and if it is of the form 2m plus if it is of the form 2m, we directly get that either of am or am minus 1 is greater than 2m or 2 into m minus 1. Now we repeat this procedure for many times, and we get on the conditions that either a1 or a2 is greater than 2 or 4, which is not true, as it is given to us that a1 is equal to 2 and a2 is equal to 4. a2 is equal to 3. Now we get to the condition. Now my next claim is that ak is also going to be greater than k. We repeat a similar type of procedure in which we assume that ak is smaller than k, and we get to the same conditions, that either a1 is less than 1 or a2 is less than 1, a2 is less than 2, which is not possible. Now we move on to the third claim, and the third claim was that for any even we cannot have a 2m is equal to 4m. Let us assume to the contrary, that we have a 2m is equal to 4m. Then we say that a 2m is equal to 2 plus am plus am minus 1. This must imply that both am and am minus 1 are equal to 2m and 2m minus 2 into m minus 1, as we have both am and am minus 1 less than 2m plus less than 2m plus 1 and 2 into m minus 1 plus 1. We repeat the same procedure, and we get on the conditions that either a1 or a2 have both a1 is equal to 2 and a2 is equal to 4, or either a1 a2 and a3 has both a2 is equal to 4 and a3 is equal to 6, In each of the following cases, we have a2 is equal to 4, which is wrong as given to us.
Yeah,
Now,
but this may not be true for smaller numbers. This could be true for larger numbers, right?
By repeating same process is
We repeat the same.
we repeat the same process until we reach one of these pairs.
Correct.
Now we move on. Now the only case left to us is odd numbers. In odd numbers, we prove that only for 2 raised to power n minus 1 form numbers we have ak is equal to 2k. We do this in the following manner. We take a binary string of ones. We write all of these numbers in binary. Let us have a n string and a 0 here and another number here. We write for any 2k plus 1 form number, we have a 2k plus 1 is equal to 2 plus 2ak. If this equals 2 into 2 into 2k plus 1, then this must imply that ak is also equal to 2k. Hence we get ak as also odd. We keep on repeating the same procedure n minus 1 times until we reach, in each time we deduct a number until we reach this number and something here which has the same properties as this number. Now when we repeat this procedure once more and we reach on to a even number. Now if this even number is not 0, we cannot claim the fact that am is equal to 2m, and hence this even numbers needs to be 0. This must imply that for all ones there is no numbers present here, and this must imply the number is of form 2 power n minus 1.